Greetings and salutations, magical chemists. Let's take a look at electrochem equilibrium under non-standard conditions. Now, you already know that standard cell potential, the E0 cell, is your cell potential measured at the standard conditions of 1 atmosphere, 1 molar solutions, and 25 degrees Celsius. However, as a voltaic cell runs, reactants are getting consumed, products are being made. Things aren't going to be at 1 molar anymore. That means as the battery operates, conditions are becoming more and more non-standard, and this causes the voltage to decrease. So let's talk about non-standard cell potential. This is where we just say E cell, no not sign. Now, technically, this just means cell potential measured at any non-standard conditions. You could change the pressure, you could change the temperature, but for us, to be honest, all we ever really change is concentration. So this is the only thing I've ever seen actually discussed, is changing the concentration so things are not exactly at 1 molar. We already know in a standard galvanic voltaic cell, it's spontaneous, right? It wants to make products, okay, is much, much greater than 1, but 1 molar solution, Q is equal to 1. So that's when you have your voltage measured at E0 cell. That's your cell potential. However, we can change the concentrations to make Q larger. This would make Q closer to K, closer to equilibrium. Remember, at equilibrium, you have a dead battery. So hopefully it makes sense as you get conditions closer and closer to a dead battery, well, your voltage is going to go down. That means your cell potential is less than your cell potential under standard conditions when Q is larger than 1. And of course, you can do the other way around. You could make Q smaller than 1. That would actually make your conditions even further from equilibrium. Well, if your current conditions are further away from equilibrium, you have an even higher driving force to achieve equilibrium. So that is going to increase the voltage. So in that case, the cell potential under non-standard conditions would be greater than the cell potential under standard conditions. So let's try to look at this visually. We already know what happens at standard conditions, where Q is 1. Q is automatically less than K, of course, since K is greater than 1 in a spontaneous reaction. And so the cell potential you're measuring is the standard cell potential. And that will run all the way to reach equilibrium when you have a dead battery. But the thing we're adding in, the new information is, okay, as you progress from your current conditions to reach equilibrium, your K value, as you make more products, is going to keep increasing. So the idea is Q is getting bigger and bigger as it approaches K. What's happening as you get closer and closer to equilibrium? You've got a lower and lower driving force. So the closer you get to equilibrium, the less measured cell potential you have relative to what you would have had at standard conditions. Of course, if you instead mess with the system and you make Q a lot smaller, either put in a bunch of reactants or take away products, now you've really increased your driving force. You are super far away from equilibrium, so you're going to have a really large measured cell potential, much larger than it would be under standard conditions. So let's summarize the changes we could make to change Q. Anything you do to bring the system closer to equilibrium, which means either increasing the concentration of products or decreasing the concentration of reactants, is going to decrease your measured voltage. And of course, if you change things in a different way to decrease Q, you're moving the system further from equilibrium, which is going to lead to a higher measured voltage. To decrease Q, you can either increase the concentration of reactants or decrease the concentration of products. Now, just a note about thermodynamic favorability, because when you're changing the voltage, you are changing how thermodynamically favorable the reaction is. So if your voltage has gone up, well, that means that cell must have a greater driving force. It is more thermodynamically favorable. But if you're getting closer to equilibrium and your voltage has decreased, that's because you have less of a driving force. The electrochemical cell is less thermodynamically favorable. Okay, Let's take a look at the type of problems you might be asked about this kind of stuff. Okay, in this particular problem, they're giving you your balanced redox reaction, and they gave you the cell potential under standard conditions. And then they said, okay, well, you're going to make a galvanic cell like this. But, not standard conditions. The copper 2+ concentration is only 0.5 molar. So the classic question, is the voltage of the cell higher, lower, or equal to the standard cell potential, and why? Well, in this case, the concentration of a reactant decreased, so the voltage of your cell is going to be lower. Let's see how we'd explain that for free response. First, we just state the answer. The voltage is going to be lower, right? Your cell potential is less than your standard cell potential. And that's because the concentration of your copper 2+ ion is less than it would have been under standard conditions. But this is not enough. We need to explain why lowering the concentration of the copper 2+ will actually lower the voltage. And so what I like to say is, well, decreasing the concentration of a reactant will increase Q, bringing the reaction closer to equilibrium. Both components are needed to get full credit on your free response. All right, let's try another one. But this time, you're going to try it. And it's even got a sneaky question built in. So it's giving you the starting concentrations and the cell potential. We are looking at the same thing. They want to know, is the voltage higher, lower, equal to standard cell potential? And here's a fun one. What do you think happens to the amount of time that this cell could operate? All right, I would like you to pause the video and try to answer this on your own, see what happens, and when you are ready to check the answer, unpause the video. Okay, this one is a little more devious, so it can be helpful to actually plug in and calculate Q. We have the information, and so you notice we have increased the concentration of both reactants and products. Well, that means that technically 2 divided by 2, our Q value is still equal to 1. That's the same value as Q at standard conditions. That means we're the standard distance from equilibrium, so our cell potential is going to be exactly the same as the standard cell potential. It will be equal. What about that second question? What happens to the amount of time this cell could operate? You might think because the voltage is the same, well, the amount of time it could operate is still the same. But actually, you have twice as many reactants. Thus, this cell could run twice as much time as a standard cell, even though the voltage is the same. Okay, part C is yet another variation of the same style of question. So I think you should read this, try it, and when you're ready to check your answer, unpause the video. Okay, this time they're making a standard cell. However, they let it run for 2 hours and then re-measure the voltage. Oops. Hopefully you realized that that means that we are going to now have a cell potential that is lower than the standard. Why? Well, as it runs, reactants are used up and products are formed, bringing the cell closer to equilibrium, so the voltage goes down. Okay, so let's summarize. Basically, if you have anything that moves your system away from equilibrium, voltage will go up. But if you move closer to equilibrium, voltage will go down. The sneaky part is recognizing that if you're increasing or decreasing things by the same factor, and they have the same exponent, then your voltage will stay the same, but it can change the amount of time the cell can operate. One important thing to note is that if you take away all of one or more of the reactants, your voltage goes to 0 because you don't have any reactions, so you don't have a current. What's interesting is if you take the solid product, which is your cathode electrode, that actually doesn't change your voltage because it's a solid, so it's not part of Q, and it's a product, so you don't need it for the reaction to run. And if you increase the amount of reactants, that's going to increase the amount of time the cell can operate, even if the voltage doesn't change. Okay, since you are not asked to do math for problems like this under non-standard conditions, you're only asked to make qualitative predictions, but honestly, sometimes that can be kind of annoying for the free response. So I wanted to go ahead and give you some example free response explanations you could refer back to for a couple of different considerations. First would be increasing reactance. Oops. That's supposed to be concentration of products. That's for the second one. So increasing reactance, the concentration of products remaining standard. The second one is saying, okay, I'm increasing the concentration of products, but the reactants are saying standard. And the third one says, hey, I'm increasing both of them by the same factor, or honestly, decreasing them both by the same factor. So this is just a summary of the three most common changes. It's totally possible to both increase reactants and decrease products, but that would have the same effect, same as increasing products and decreasing reactants. So this way you have a sample free response explanation of each to refer to as you are practicing. Speaking of practicing, hey, look at that. We've got this amazing example to practice. Now, some of it is a little bit of review, some of it is not, some of it is just lots of tasty and delicious fun. So yes, you know what you're going to do. You're going to pause the video and you're going to try all of this together, putting all the parts together on your own. And when you are ready to check your answer, unpause the video. First things first. Well, we're making a galvanic or spontaneous cell, and that means whichever half reaction has the more positive, or in this case, less negative reduction potential, gets reduced. So lead is going to get reduced, which means cadmium, we've got to flip that to get our oxidation half reaction. So the anode half reaction will show cadmium being oxidized, releasing 2 electrons. The cathode half reaction will show lead 2+ being reduced and gaining 2 electrons. And hey, for the balanced reaction, pretty nice, the number of electrons being transferred is already equal. So electrons cancel out and everything's got a 1-to-1 coefficient. Okay, now finally we're getting back to that non-standard conditions, right? Because they did tell you it's a non-standard cell. The concentration of the cadmium was 0.01 molar and Pb2+ is 0.1 molar. Eek! Now you'll notice it was essential that we had the balanced equation because otherwise you didn't know which one of those was a reactant or a product. And flipping this would totally change the answer. Okay, technically speaking, we've reduced the concentration of both of these things to less than standard conditions, but we made one smaller than the other. So if we plug into Q, when we calculate our quotient, since we decreased the concentration of products more than we decreased the concentration of reactants, that gives us a value less than 1. Less products means the reaction is even further from equilibrium than under standard conditions. So that means the cell potential is going to be greater. And there you have it. There's a really fascinating application of this non-standard equilibrium called a concentration cell, because you can actually make a galvanic cell by using 2 cells that have the same metal ion concentration. Notice, solid copper, copper 2+, solid copper, copper 2+. Well, under standard conditions, there's no voltage, right? Because they're equal. However, if you start one off at a lower concentration and the other at a higher concentration, electrons flow from the lower concentration to the higher concentration to achieve equilibrium, basically to make the concentrations equal. That means the lower concentration half cell will always be your anode, the higher concentration will always be your cathode. So let's see, can you design a galvanic cell using a 0.2 molar zinc 2+ solution and a 0.05 zinc 2+ solution? Go ahead and draw this out and then label all of these things. And when you're ready to check, unpause the video. Okay, the first thing I did was put in the stuff I knew had to be there, right? It's entirely made out of zinc. There's a salt bridge connecting the two. So it doesn't really matter which side you made the anode and which side you made the cathode. As long as you realize that the lower concentration is your anode and the higher, oops, I didn't write down the right concentration. There we go. Now the higher concentration is going to be your cathode. The reason is that in the drive for basically equal concentrations on both sides, you need to increase the concentration of zinc 2+ on the anode side. Well, when that happens, it's going to be giving up electrons that are going to transfer to the cathode. As the cathode is gaining those electrons, the zinc 2+ is being reduced and turning to solid zinc, decreasing the concentration of zinc in that solution. And there you have it. All the glories of non-standard equilibrium for electrochemistry. So thank you for playing with the glories of chemistry.